So thank all of you for getting up so early to see this talk. Uh, if anyone has questions, you should speak up. I understand that people in St. Petersburg are shy, so don't hesitate uh, to raise your hand if something is unclear. So I'm going to start with the obligatory picture of Moore's law. Every lecture has to have a Moore's law picture, so I'm going to do this right away so we can move on to other things. So for a long time, whenever you would buy a computer, it would run faster. Every year, it would be twice as fast as previous years, and this made life very easy for people who wrote software. You could add new features, which would slow down your program, and 6 months later, nobody would notice. Then around 2000, things started to change. It was no longer possible to make computers run faster. It was still the case that the transistors were getting smaller, but you couldn't make them run faster. Now, people who do electrical engineering can give you all kinds of technical reasons, but the actual reason is very simple. That is, beyond a certain point, the chips just get too hot. So if you make your transistors smaller and you run them faster, then they catch on fire. And so you have to stop increasing the clock. But what you can do is you can provide more cores. So every year we have more cores, but they don't run any faster than they did before. So except in devices like smoke detectors, you're unlikely to find any machine that has only one core anymore. It's cheaper to make more than to make and not use them than it is to make a single core machine. In the early days, it was common to build what were called shared memory multiprocessors, where you would have a memory chip and then you would have multiple processor chips. Nobody does that anymore either. And instead, we have what we call a multicore processor, where all the processors and the memory and the caches and everything else are on the same chip. So this means that communication between the processors can be very fast. It means we can put a relatively large number of processors on the same chip. So we end up having lots of concurrency. And every year we have more and more concurrency. And the reason this is interesting is because nobody actually knows the best way to take advantage of this. This is why I still have a job, is because nobody understands this problem. And so I can come to beautiful places like St. Petersburg and talk about how to solve these difficult problems. Now, this is an old-fashioned machine by now. But you can see that each of those little rectangles there is a processor, and everything else is a memory cache and an interconnect. Now, again, in the old days, when you would wait for some amount of time, your processors would become more powerful. So this slide is a little misleading because I have a more powerful processor shown as a bigger processor, but actually it's a smaller processor. But I think you get the idea. And so what happens is that your code remains the same, and your speed up rises. So this is sometimes called the free lunch, because you don't have to do any work to get improvement. So you can take something like Word and you can add spell checking. Then you can add this feature and that feature, and you don't have to do anything. You sit back, wait 6 months, and everyone is happy. Now, what you would like to say is, well, now that the clock speeds are the same, now that the processors don't run any faster, but we have more of them, then no problem. We start out with 2. Next year, we can buy a server with 4. Next year, we buy a server with 8. And our speed up should go ahead. And everything should be the same as before. Now, this is an idealized view of the world. The actual view of the world is much more difficult because you need to be able to coordinate and synchronize all of these worker threads. So usually when I'm at a party and someone asks, well, what do you do? I say, well, suppose you just bought an apartment that has 4 rooms and you want to paint them. So you invite your friends over, give them pizza. And you have 4 friends, and no problem, each one paints a room. Now suppose you have 8 friends in 4 rooms. Well, it's a little bit trickier. Now imagine you have 10,024 friends and they're not very smart, and they come over and they want to paint your 4 rooms. And they end up painting each other and painting over the windows and things like that. So you have to be able to find an efficient way to get your not very smart but very industrious friends to coordinate to get a job done. And this is ultimately the subject of most of concurrent computation. So what happens is that the costs of synchronizing and locking and other kinds of overhead start to dominate. And the parallelism that you get, if you're not careful, doesn't do you much good. So all of this requires great care. Now, we can talk about this a little bit more systematically with something called Amdahl's law. Now, Amdahl's law is, again, don't take this literally. This is not really a mathematical formula. It's a way of thinking about how different trends interact. So don't try putting in numbers, because this is really not actually science. So the speed up that we get from buying a more parallel machine is the ratio of what happens if we do all our work in one thread versus what happens if we do all our work in n threads, where n is the number of processors that we have. We can break this down a little bit further and say, well, let's normalize and say, well, the amount of work that one thread takes is 1. And we can say P is the fraction of the work that can be parallelized. Not all things can be made parallel. Some things have to be done sequentially. Now, the parallel fraction, we can take it and we can split that up among the number of threads. So this is good because it says this amount of work we can take and we can divide it up evenly. And all of those threads can go do that work in parallel. And part of it is sequential. Yes? You're right. That's a bug. So this is henceforth 1 minus p, and that is a part of the work that cannot be sped up. That simply cannot, either for practical reasons or mathematical reasons, cannot be made to go faster. Now, as I said, this is pseudo-mathematical. The one thing to understand from Moore's law is that if your synchronization is bad, if that 1 minus p part is large, then nothing is going to work. That you can be extremely clever, but if the synchronization and coordination part of your multicore program is poorly engineered, then you are not going to have a good day. So, some examples. So, your boss goes out and he buys a 10-core machine and says, okay, your job is to make this work. Your job is to make me look good by speeding everything up. And so you take your application, you say, well, my application is 60% concurrent. That's really good, because it's more than half of it can be made parallel. And only 40%, a minority of the work, is inherently sequential. Or I don't know how to parallelize it, or I didn't bother to parallelize it. And the question is, how much speed up do you get? How close to a 10-fold speed up? And the answer is not very good. So now your boss gets angry. He says, look, I spent all this money on buying 10 cores, and you deliver me 2-fold speed up. This makes me look very bad. So you better get to work and fix this. So even if a majority of your program is parallel, then you won't do very well. Okay, so you go and you make your programmers work all night, and they say, okay, they come back and they say, okay, we're now 80% concurrent. We went from 60% to 80%. So surely this must be pretty good. And how close to a tenfold speed up do we get? Well, it's pretty simple. Now you're 3.5 times. So after all this work, getting 80% parallel, your 10-core machine is only 3.5 times better than your old 1-core machine. So you paid for 10 processors, but you're only getting 3.5 of them. Okay, so you go back and you tell your programmers, you've got to do better than this, so we're going to fire you, we're going to throw you into the Nieva, we're going to do all kinds of terrible things if you don't make this run faster. So they finally get 90% concurrency, and now we're up to basically 5 processors. So the thing to understand here is that Moore's law is, Amdahl's law is very unforgiving. That even a little bit of non-parallelizable part of your program is going to slow things down by an enormous amount, because the non-parallel part always dominates the rest of it. And this is why for a long time people didn't care very much about concurrency, because it's hard work to get benefit from concurrency. They said, why should we spend so much work to make our programs concurrent when our processors became faster? But now that our processors are no longer faster, we have no choice. We have to focus on concurrency. So finally, the good news is that if you're 99% concurrent, then you'll get a 9-fold speed up, and you can keep your job. But as you can see, the need to make even small improvements in the concurrency will have a big effect at the end. So this is why the study of concurrent algorithms and synchronization is important in the real world and not just in theory. So what I'm going to talk about are the parts of the concurrent program that involve synchronization and coordination. Now, there are many applications, particularly scientific applications, where coordination is not so important. You want to multiply 2 huge matrices. Well, there's very little synchronization that you need to do. And that's fine, but we don't care about that. But if you're writing a database, if you're writing a file system, if you're writing a blockchain, if you're doing anything that involves interaction, then this could be important. The analogy that I use is you can go out and you can buy a carbon fiber Italian bicycle with very expensive parts, but if the ball bearings aren't any good, then it doesn't matter how well the rest of it works. And what we are going to look at are basically the ball bearings of your Multicore software. Okay, now, normally I talk about this material at the end of a long course where we talk about concurrent data structures, locking, lock-free, wait-free, all kinds of different synchronization techniques. And then I say, well, when we get to the end of it, the foundations of the field are still imperfect. So in many areas of computer science, we have layers of abstraction that work very well. So you almost never think about virtual memory. When you start your laptop, if you don't have enough memory, then it moves things smoothly between the disk and the main memory, and you never notice it, you never think about it. Unless you're really doing extremely specialized work, it's hidden. In the concurrent world, we're not able to do that. We need to understand how things work basically from the top to the bottom, because the field is still too young and poorly structured to be able to give us the kind of protection that abstraction gives us. Now, when you're building a concurrent data structure, there are a number of ways that you can do this, and these are covered in this book. But ultimately, they're imperfect. The foundations of the field are not what they should be. And I'm going to tell you what the problems are with the way that we do things now. Now, in many cases, you don't have any choice, and you have to use these imperfect mechanisms. But I want to focus for a moment on what's wrong with these. So typically, you want to build a concurrent hash table, for example, or a concurrent tree. The usual technique you use is locking. So this is like in a bathroom. You go inside, you lock the door, and no one else can use it while you're using it. When you leave, you unlock it. Now, the easiest way to do things is you put one big lock on your entire data structure. For many years, the Solaris kernel had a single lock on the entire kernel. And Sun was quite happy with this because there weren't very many multi-core, multiprocessor machines, and so nobody cared. Then, for several years, they were aware that this was a bad idea and a bad design, but everyone was too frightened to change it because nobody actually knew how it worked. What everybody knew was that there was one bit in memory where if you lock that, then you were pretty sure that nobody else could be inside the kernel. And it took them several years before they could come out with a new version of the kernel that didn't have this problem. So this is this has the advantage that it's easy to make this correct. You just say, before you do anything dangerous, make sure that you acquire this lock. The problem is, of course, that it's not scalable. There's no concurrency. There's a lot of contention for locks. There's a lot of unnecessary synchronization. But the fact that it is easily made correct is not something that you want to take lightly. So alternative to coarse-grained locking is fine-grained locking. So you say, well, instead of putting a single lock on everything, I'm going to put lots of little locks on my data structure. And you only lock the parts of the data structure that you're using. So if I'm using one part of the tree and you're using a different part of the tree, then we can work in parallel as long as we're not touching the same pieces. So this is intuitively appealing. It seems like a better idea, except for the fact that if you've ever tried this, you know that this can be very difficult to make this correct. People are not very good at reasoning about concurrent activities. And so I've seen many cases where you write some code, you look at it and says, this is obviously correct. You run the code and a week later something goes wrong. And your friends come in and they look at it and they scratch their heads and finally somebody says, oh, look at these two lines. This is, you acquired the wrong lock or you forgot to acquire a lock. Or you have a deadlock. All kinds of bad things can happen because writing programs with lots and lots of locks and lots of protocols about the order in which you acquire locks is difficult to do this correctly. There's another problem, which is basically a performance problem, which is that locks are not robust in the following sense. That if a thread acquires a lock, and then let's say it crashes, it gets swapped out, it gets cache miss and it's delayed, then every other thread that wants to use that resource is locked out. It's like having a 2-year-old that walks into a bathroom, locks the door, and falls asleep. Then nobody can use a particular resource. And in multicores, this happens a lot because you can take page faults, you can take a cache miss, the processor might decide to page you out and bring in another thread. And so even if you don't actually crash, you are subject to very long and unpredictable delays. And if you're holding a lock when this happens, then everyone is delayed, even if they're capable of doing work. So this can be a serious performance problem. So if a thread holding a lock is delayed, no one else can make progress. There's another problem with locking that people don't talk about much in academic classes, but this is something where if you've ever written a multi-core program, you're probably aware of, particularly if you're fixing someone else's code, and that locking relies on conventions. That is the relation between the lock data and the object being locked exists only in the mind of the programmer. So languages like Java and C# to a lesser extent try to associate locks with objects, but that never works very well. And so in the end, what happens is you write down on a piece of paper, before you do this, acquire this lock, release it, and then acquire another lock. And what happens is that you end up with very fragile programs that no one understands. For example, a friend of mine found this wonderful comment in the Linux kernel. And I want you to take a second to look at this and admire it. Don't try to understand it, because I don't know what this means either. But it was probably written in the 1990s by some Finnish teenager writing a device driver. Who knows if it's true, if it was ever true. But I know I would be very, very nervous if I were writing a program that was touching this data. And this is this is not really a very systematic way of building up software, to rely on comments and conventions and other, writing notes on a piece of paper and leaving them under a rock, basically. So, this is not a systematic engineering approach to solving our problems. There's another problem with conventional synchronization, which is hard to make precise in a scientific way, but I think you will all understand what I mean when I say that writing highly concurrent data structures is difficult. Let me give you a simple example. I want to build a highly concurrent double-ended queue. Maybe I want to make this lock-free. Maybe I want to use fine-grained locks. That doesn't matter so much. But what I notice is that if I have two threads that are working on opposite ends of the queue, and the opposite ends of the queue are far apart, then they should be able to proceed with no synchronization, no interference. Because after all, neither one of them is affecting the other one. So why should they do expensive signaling, locking, etc.? Now, if the queue is small, imagine there's only one item in the queue and two threads want to dequeue it, then of course they should synchronize with each other, because this is logically necessary. And this is a simple problem. No synchronization if the ends of the queue are far apart, necessary synchronization if they're close together. But if you could come up with a nice simple solution to this problem, then you could probably publish it in a conference. Maybe not the best conference, because a solution has already been published in a conference. Now, what bothers me about this is that this is an example of a problem that is simple enough you could explain to a high school student, but difficult enough that you can publish a solution. Now, our friends in mathematics have many, many problems that are very simple in this state, but take centuries to solve. All these number theoretic problems. And if you talk to the mathematicians, they're proud of this. They view this as a demonstration of their superiority. But in computer science, I think we should not be so happy that we have simple data structure problems that are very hard to solve, because we're supposed to be an engineering discipline and we're supposed to be doing useful things. And it would be better if simple problems had simple solutions. If academics like me had to publish solutions to difficult problems instead of simple problems, that would make the world a better place. Okay, finally, I think the worst problem with conventional locks is that they're not composable. So one of the first things that you learn in your first year programming class is that if you need to call cosine, you don't need to write your own cosine program. You don't need to go learn about Taylor series and floating point numbers. There's a library. And I can call cosine here, and I can call cosine there. And I can call it any place that I need cosine or sine or any of these things. And I can compose these things. If I need tangent, I can call cosine and sine and compose them. And in this way, we can build up layers of abstraction. We can build powerful systems from weaker systems, all the usual software engineering story. But none of this works when we start talking about concurrent objects. So here, I have a very simple problem. I have two queues. And what I want is I want to transfer an item from one queue to another. Perhaps the most basic thing you can imagine for two data structures. Now, I want to guarantee that this transfer is atomic. I don't want to see two copies of the same item. I don't want to see 0 copies of an item. I want to guarantee that at any time, each item is in one queue or the other queue. And the problem is that this is surprisingly difficult if you, for example, try to write a Java program to do this. Perhaps the correct way to do this is first you lock one queue. Then while you're holding that lock, you lock the second queue. And now you have both of these objects locked. You do the transfer. And then you unlock the queues. So that seems fairly simple. But if you think of this from the perspective of a language like Java, there's no really convenient and safe way to do this. Because most programming languages encourage you to use internal synchronization. So when you call a synchronize method, for example, in Java, you call the method, it acquires a lock on the object, you execute the method, then when you return, you release the lock. And this is considered good software engineering practice because it guarantees that you release the lock when you return and you don't forget. Because it could be disastrous if you return from a method and you forget to release a lock. But in this case, we want to hold on to the lock. So the built-in mechanism that Java gives us is no good because it doesn't give us the ability to acquire a lock and retain the lock after we make the call. So you can say, well, no problem, I'm going to export lock and unlock methods. But that's a bad idea too, because now what happens is instead of saying this is an atomic FIFO queue, you say this is an atomic FIFO queue with lock and unlock methods, and you'd better make sure that you lock it yourself and you unlock it. And the library will behave correctly only if the clients of the library behave correctly. And this will make your system much more unstable and much more complicated, much more difficult to understand if your object specifications have to include all these synchronization protocols. So in one case, we have a clean, nice, clean, elegant structure that is too weak to do what we want. In the other case, we have a very powerful structure that is much too dangerous. It's like cutting your nails with a saw. If you build your libraries like this, you will have long-term difficulties. So exposing complicated locking protocols to clients is not a good engineering practice. And relying on clients to follow protocols is a bad idea. Everyone I know who writes software is convinced that the people who consume their software is not as smart as they are. So you don't want to write something very clever and then give it to someone who's not as smart as you because they'll break it. So this reinforces the theme that in much of the progress that we made in operating systems and file systems and programming languages is based on finding the right abstraction. But in concurrent computing, we don't have the right abstractions. So whether you like it or not, you have to be able to understand things that you would probably rather not have to understand. Final problem. Now, synchronization is different from sequential programming, often because you need to wait for things to happen. Now, in lock-free and wait-free data structures, we try to avoid waiting for things that we don't need to wait for. But sometimes you just need to wait. I'm waiting for a message. Being lock-free or wait-free is irrelevant because if I have no message, there's nothing to do. So I can have a thread here that's waiting for a message to show up in a buffer. And there's nothing there, so it goes to sleep. It says, okay, there's no work for me to do. I'm wasting electricity by running. Just put me to sleep. Tell the operating system to run something else and wake me up if anything happens. So when something happens, the thread wakes up, consumes the item, and goes on. So this is fairly standard. Anybody who's written a network protocol is familiar with this. But the important thing here is if the buffer is empty, you want to wait. Now, if you take, for example, Java or C# or C++, and you look at their synchronization methods, most of the high-level methods have the property that we cannot compose these constructs. There are ways of waiting for multiple things if you're writing low-level C code and things like that. But if you're using monitors, which claim to be more powerful, more abstract mechanisms, it turns out to be impossible to wait on more than one buffer. So in particular, if you look at Java wait and signal constructs, there's no way that you can compose two waiting activities. I can wait on one thing, I can release the lock and go to sleep. I can be woken up, but I have to wake up on the same thing. So what I would like to do is thread comes along and it says, well, my first buffer, empty, nothing to do. My second buffer, empty, nothing to do. I want to go to sleep and I want to wait for either one to show up. And as soon as something shows up in either of the two buffers, then I want to wake up and consume that item. But there is no easy way to do that in modern high-level languages. You have to drop down to C and use select and very low-level complicated things like that. So what I'm going to do next is I'm going to propose a way to solve these problems. This is an approach that is slightly controversial. It used to be very controversial, but now it's more widely accepted. And it's based on the following observation. Now, this is kind of a embarrassing secret, which people don't like to talk about. But nearly every important idea in systems and programming languages was invented by people who do databases. And it was invented by people who did databases back in the 1980s and 1990s who worked at an IBM laboratory. Now, when they wrote their papers on this subject, they wrote it in 1980s era IBM jargon, which nobody understands. It's very hard to read these papers. I don't think it's an Indo-European language. They have different words for everything. But the idea that they invented that we are going to steal is the notion of an atomic transaction. And atomic transactions, show up in lots of different places. Sometimes they have different names. But this is the one basic idea that we're going to take from them. So I'm going to in order to dramatize this a little, I'm going to say, this is a manifesto. We're going to revolutionize. This may be, I don't know if this is a good place or a bad place to say this, but we're going to revolutionize the practice of programming. So what I've tried to establish so far is that standard techniques, they work well enough that we could build software, but they don't work the way they should work. In particular, they don't work as well as other constructs in other areas of computer science. And we need to think about things differently if we want to fix these things. So our agenda is to replace locking and to some extent lock-free and wait-free data structures with an interface that uses atomic transactions. And I'll explain what atomic transactions are a little bit later on. So we want to replace locking with transactional API. We want to design language support and libraries to make this kind of programming accessible. So typically, languages are fairly simple things. Libraries, we get very clever people to write libraries which do all kinds of crazy things underneath, but present a nice clean interface to regular programmers. And then we need to talk about efficient runtimes. Now, I'm going to talk about the first and third items here. I'm not going to have too much to say about languages because this is still kind of unexplored area. Right now, if you want to write transactional programs in this style, you have to use C and C libraries. There has been some progress in, actually there's been a lot of progress in C++, less in Java and C# and similar languages. So roadmap, what I'm going to do for the rest of the talk is I'm going to talk about this idea called transactional memory. I'm going to first talk about hardware support for transactional memory. This is where this whole effort began. I'm going to talk about hardware not because I expect anyone here to become a software engineer and start laying out wires on circuits, but because in order to understand how to use modern transactional memory libraries, you need to understand how the hardware works. Because as I mentioned, all of the abstractions are broken, and we can't treat the lower level layer as a black box because things will break and you won't know why. So unfortunately, it's necessary to understand how the hardware works in order for your software to work well. Then I'll talk about something called hybrid transactional memory, which is a way of taking hardware and improving it with the software layer. And I think most current transactional programming is done in kind of a hybrid context. And then I'll talk about software transactional memory, where everything or most of it is done in software. This is an area that has has received a lot of attention. I think it's still, there's still work to be done to make this really work well, but it's important to understand, again, how this works if you want to write programs in this kind of area. Okay, then I'll talk about research questions. All the things that we don't understand, all the things that we would love to be able to fix. Okay, so let me first start out by telling you what transactional memory is. So what's a transaction? Well, for our purposes, a transaction is just a block of code that appears to execute instantaneously. So you write a sequence of statements, and they all happen at once. Of course, the truth is a little more complicated, but this is good enough for our purposes today. So one way to think about this is to borrow terms from databases and say that if we execute many transactions in parallel, the result is serializable, which means that it appears that they happen in a one-at-a-time order. Now, in practice, we want them to happen concurrently, but sometimes they interfere with each other, and when they interfere with each other, we say we don't want them to interact like this, with complicated races and so on. We say that they must appear to have happened, either one happened first or the other happened first. So there is no apparent interleaving. So we want things to happen in parallel for real, but we want things to appear to happen in one-at-a-time order because it is much easier to program if you only have to worry about one thing at a time. If you have to worry about the number of ways in which two parallel programs can interfere, that's huge. And people are not good at this kind of reasoning. If they happen in a one-at-a-time order, then there is some hope that that people will be able to understand this. So typically when we do execute a transaction, we will execute it speculatively. Speculatively means we basically try to do everything. Yes? So it's almost the same thing, but not exactly. So linearizable says that if you have two individual operations, say 2 NQs, then they happen in they appear to happen in one-at-a-time order while they were being called. So serializable says if I have these multi-step transactions, then these multi-step transactions appear to happen in one order or the other. Typically, there's no requirement that the serializable transactions happen in real-time order. In practice, they often do, but technically, not necessarily. But it's still the same basic idea that you want to take things that could interfere in complicated ways and simplify them by saying that it looks like they happen in a one-at-a-time order. So it's a little bit confusing, but database people often say serializable when they mean linearizable. And sometimes even my friends in distributed computing say linearizable when they should have said serializable. But, you know. Typically we execute these things speculatively, which means that we make tentative changes, and then if everything is okay, then we say we commit the transaction, we make its effects visible to the world. If something goes wrong and there's a synchronization conflict, then we abort the transaction, which means we undo it and nobody ever sees its effects. So we're going to be talking about commits and aborts. You know, commit is success, abort is failure. So in my examples, I'm going to use a simple keyword that doesn't really exist in any language. The C++ standard has something called __ atomic, which is similar. But the idea is that I could put these compound statements inside an atomic block, and everything between the begin and end happens atomically. And in particular, you know, here I remove something from X. Here I add it to Y, and here I null out Y. And these Ys are the same. If you wrote that in a C++ program, this would be incorrect because you're accessing a Y without synchronization. If you write this with atomic blocks, then it's okay. Then there is no data race. So you remember the double-ended queue problem that I talked about before, how this was difficult, and if you wrote a lock-based solution, you could publish it in a second-rate conference. Given an atomic statement in your programming language, here, for example, is a sequential double-ended queue. So I write the sequential code, I put an atomic block around it, and now I've solved the problem. So at this point, the transactional machinery underneath will decide how to do the synchronization, but I as a programmer say, I want this to happen atomically. I don't need to worry about how this is done. I'm going to tell you a lot about how this is done in a minute. But from a programmer's point of view, this is very simple. You know, a child could do this. So the problem that we had before with locking is easily fixed if we have this atomic keyword. Yes? I'm going to try to avoid talking about the Java memory model as much as possible. But so here, assume that the memory is sequentially consistent. The atomic would actually have the same semantics as a synchronized block. So when you enter it, you flush everything, and same when you leave it. Yeah. And so that's a good question, which I'm going to try to avoid. So we close things in atomic blocks, and our simple problem now has a simple solution.